Hello and welcome back. So in the last few lectures, we have learned about different aspects of aluminium and aluminium alloys. We started off with pure aluminium and we had seen the different properties of pure aluminium and so on. And then we started talking about the aluminium alloys. And with regard to the alloys, we have seen different aspects such as the alloy designations, and here we talked about the aluminum association designation as to how the alloys are given a particular number to identify them in terms of their compositions. Okay, and then we have discussed about types of aluminum alloys such as wrought alloys and cast alloys. Okay, so wrought alloys are the ones which are subjected to some secondary processing after their cast. Okay, so after they are processed, the billet which is obtained from the primary processing, it is subjected to some kind of metal forming process which will give rise to a product which is known as the wrought product. So that can be, for example, a rolled sheet or an extruded rod and things like that. Okay, so these are known as the wrought products or the wrought alloys. Then we talked about the cast alloys as well, and we have also seen how the cast alloys are designated. Okay, and in the cast alloys we have seen a very important alloy, that is the aluminium silicon alloys. And here we have discussed about the hypoeutectic aluminum silicon alloys and the hypereutectic aluminum silicon alloys. Okay, so anything below 12.6% silicon, as you have seen, will be under the category of hypoeutectic alloys, and anything beyond 12.6% silicon will be hypereutectic. Okay, and here we have seen how the silicon phase grows in a particular morphology. Okay, and how that can be modified to improve some of the properties such as the ductility and the toughness. Okay, so we have discussed in detail the morphology and the growth of silicon, and we have also seen the mechanism of modifications so that this morphology which is detrimental can be modified to a morphology which is beneficial. Okay, so all that we have discussed in previous lectures, and now that we have gained some understanding about aluminium and aluminium alloys, let us go ahead and see the other aspects of aluminium alloys, particularly with regard to the physical metallurgy. So from now on, whatever we are going to talk about, it will be mostly centered around the physical metallurgy of aluminium alloys.
Now let us have a look at the aluminium alloys from a physical metallurgy perspective, where we will try and understand as to why these alloys are stronger. Right? Because you have already seen before, while we discussed about the properties of pure aluminium, is the fact that the mechanical properties or the strength of pure aluminium is quite low, and that is why we have the need for aluminium alloys for applications where you need higher strength, right? So therefore we need to understand as to why these alloys become stronger when you have presence of certain alloying elements. Okay, and this is also kind of the start of our physical metallurgy part. The physical metallurgy of aluminium alloys. Okay, so we need to understand the mechanism of strengthening. Okay, so this will be our first topic with regard to physical metallurgy of aluminium alloys. Okay, and we'll start with solid solution hardening or solid solution strengthening, because right now we are talking about alloys or solid solutions. So let us try and understand as to what is the mechanism of strengthening in the aluminium alloys. So I suppose when you talk about strengthening, you know that we need to go back to the dislocation theory, because anything to do with deformation of metal, plastic deformation of metals, the dislocations will always come into picture, because as you may know, the plastic deformation of metals occurs through a process called slip, which takes place by movement of dislocation, right? And this movement happens on a particular plane known as slip plane. And also you have a particular slip direction, and in fact these two put together give rise to what is called a slip system. Okay, so slip is the process which is responsible for plastic deformation of metals, right? So anything which can retard the motion of dislocations will actually increase the strength, because then you need to apply more force or higher stress for the dislocations to move, and therefore the strength will increase. Okay. So any resistance to dislocation motion will increase the strength. So now that alloys are stronger, or solid solutions are stronger compared to the pure metal, you can say that addition of this solute or the alloying elements hamper the motion of dislocations, right? And that is why the solid solutions or alloys are stronger. But we still do not know as to how do they do that. I mean, how do they restrict the motion of dislocations? And that is something that we need to understand in order to understand this mechanism. Okay. So in order to understand that, we need to first understand as to what happens when you add the solute atoms, the alloying elements, to the parent lattice. I mean, what happens to the parent lattice when some of these parent atoms are replaced by the solute atoms. Okay. So here there are two scenarios. One, the solute atom is bigger than the parent atom, and second, it is smaller than the parent atom, right? So in either case, it will induce a lattice strain, because the size is not matching with the size of the parent atoms.
So, solute atoms will introduce lattice strain as their size is different from the host atoms. A larger substitutional solute atom, for example, will impose a compressive stress as is shown in figure A. So, if a host atom is replaced by a larger solute atom, then you can see that it will displace the atoms around it, and that will create a compressive stress on the surrounding lattice as being shown by these arrows. Okay. On the other hand, when you have a smaller substitutional atom, that will cause a tensile stress, as you could see from figure B over here. So when the host atom is being replaced by a smaller substitutional atom, then this space which was occupied before by the host atom is now occupied by a smaller atom. So when these parent atoms surrounding it try to fill up that space freed by the smaller substitutional atom, you can see that this is going to create some kind of tensile stress on the surrounding lattice. Okay, so that is how the substitutional solute atoms will create some kind of strain field in the host lattice. A larger atom will create a compressive stress, and a smaller atom will create a tensile stress field in the surrounding host lattice. Okay, and interstitial atoms are often bigger than the interstitial space they occupy, and therefore they will result in a compressive stress field. So due to this stress field associated with solute atoms, they will interact with the dislocation, because the dislocation also has a strain field around it. So just above the dislocation line, it is a compressive field, and just below it, it is tension, as you could see from this diagram over here, right? So above it is compression, and below it is tension. So therefore, a solute atom which induces a tensile stress in the lattice will be attracted to the compressive region of the dislocation, that is towards the upper side of this dislocation line, right? So that's what you can see over here. The smaller atoms, smaller solute atoms which induce a tensile stress in the host lattice will be attracted to the compressive field, right? And this will basically nullify part of the compressive strain field of the dislocation, which will ultimately reduce the strain energy, right? So you can see that smaller solute atoms will be accommodated in the compressive field above the dislocation line or above the slip plane. Similarly, the larger solute atoms which induce a compressive field will be accommodated below the dislocation line to nullify part of the tensile stress field that the dislocation has in that region, right? So solid atoms with a tensile strain field will diffuse to the dislocation core to nullify part of the compressive strain field of the dislocation, and as I said, this will reduce the strain energy, right? Similarly, solid atoms with a compressive stress field will diffuse to the tensile strain field region of the dislocation core, and that is how the motion of the dislocation will be restricted. Okay, and that in turn will increase the strength of the metal, because any hindrance to the dislocation motion will require higher stress for the dislocations to move, and therefore the strength will increase. Okay, you can see the result here. When a certain amount of solute is added to a pure metal, the strength increases, right? So here C1 and C2 indicate the concentration of solute, and C2 is greater than C1. So as you can see, as the concentration of solute increases, the strength also increases. So this phenomenon is known as solid solution hardening or solid solution strengthening, because it is coming from the formation of a solid solution due to addition of solute atoms which hinder the motion of dislocations.
But we still need to understand as to what exactly happens when the solute atoms diffuse to the dislocation core. I mean, you need to understand what kind of interactions will take place between the solid atoms and the dislocations, okay, which will ultimately lead to restriction to dislocation motion. Okay, so let us try and understand that. So that's the second part of this particular mechanism as to how the solid solution strengthening takes place. One, of course, is this kind of interaction, the attraction between the compressive stress field and the tensile stress field that the solute atoms induce, or the tensile stress field of the dislocation and the compressive field of the solid atoms. So this is attraction between tension and compression. That's what leads to the restriction to the motion. But what exactly happens, that also we need to understand, as I said. Okay, so that's the second part of it. So let us discuss that and try and understand the interactions. So this part will give you little more understanding, as to what is going to happen when you have the presence of these solute atoms and when the material is being loaded. So first part is, of course, it's the elastic interaction, what we have already discussed, right? That means the opposite forces attracting each other. Compressive field of the dislocation attracting the tensile field of the solute and vice versa. So this is one thing that is definitely going to happen because, as I said, the solute atoms will introduce some kind of strain field into the lattice. And this basically arises due to the atomic size difference that we already talked about. Right? You know the Hume-Rothery rules, and there is a certain amount of difference in the size. Up to a maximum 15% of difference can be accommodated as per the Hume-Rothery rules. We all know that. Right, so due to that size difference, it introduces some kind of strain into the lattice and that restricts the motion of the dislocations. And that is what just now we have discussed. Okay, right. So elastic interaction is all about the interaction between the solid atoms and the dislocation due to the difference in the atomic size. Okay. So this is one of the mechanisms by which the solute atoms and the dislocations interact. The second mechanism is the modulus interaction. This arises due to the fact that the elastic modulus of the parent metal and the alloying element is different, and due to that, when the solute atoms are added to the parent metal, the modulus will change locally. Right? And this will also lead to an attraction between the atoms, the solute atoms and the dislocation. Especially when the shear modulus decreases. the dislocations will tend to attach to these regions where the modulus, particularly the shear modulus, decreases. And that is how, this attraction, that means the dislocations going towards this kind of regions where the modulus decreases will lead to the restriction of the motion of the dislocations, and that is how the strength is going to increase. Okay. Modulus interaction is similar to elastic interaction. But one thing that you should remember here is the fact that for elastic interaction, the substitutional solute atoms can interact only with edge dislocations. So as you know, there are two kinds of dislocations, edge and screw. The strain field associated with substitutional solute atoms is more symmetrical. You can say it is kind of spherical, and therefore the solute atoms of this nature, that is the substitutional solute atoms, will interact only with edge dislocations. Because in case of screw dislocations, the strain field is almost pure shear, and the strain field associated with the substitutional solute being spherical will not be able to interact with such strain fields associated with the screw dislocations. The interstitial solute atoms, on the other hand, can interact with both edge as well as screw dislocations, because the strain field associated with the interstitial atoms has both shear and dilatation components, right? So interstitial solutes can interact with both edge as well as screw dislocations. And modulus interaction can also occur for both edge and screw dislocation. Right? So as I said, modulus interaction is similar to elastic interaction, and this can happen for both type of dislocations. The next one is known as stacking fault interaction. This happens when the dislocations split into partials, because sometimes the movement of dislocations can happen in different manner, and due to that, one dislocation having a particular Burger vector, let's say B1, can dissociate into two partial dislocations with Burger's vector B2 and B3. Okay, so this kind of dissociation of a dislocation into two partials leads to a stacking fault in this gap. I suppose you all know what a stacking fault is. This is again a crystal defect which arises if there is a disturbance or distortion in the stacking sequence of the planes. Okay. For example, in FCC lattice, we know the sequence is ABC, ABC, right? So if this ABC sequence somehow is disturbed, then that will give rise to a defect or a fault known as stacking fault, right? Now, the solid atoms which are added might have some preferential solubility to this stacking fault region because the structure of the stacking fault region is different from the parent metal. Okay, so if you talk about FCC lattice, while the parent metal is FCC, the stacking fault will become ABAB because because of this stacking fault, which will remove, let's say, this C layer, so it might become ABAB, and ABAB stacking is nothing but a hexagonal closed packed structure, a HCP structure, right? So while the lattice is FCC, this is HCP, and therefore the solubility of the solute atoms is quite different in the stacking fault than what you have in the parent metal, right? So therefore the solid atoms might preferentially segregate along this stacking fault, and therefore the constriction of these two partials into a single dislocation again will be difficult due to the presence of these solute atoms along this gap. Okay, so this dislocation can only move again when you reduce this width, which is known as the stacking fault width. Okay, you have to make it really narrow so that it again kind of becomes a single dislocation, then only this can move. Okay, larger this width, it will be more difficult to move the dislocations, right? And that is what happens when these solid atoms are preferentially segregated along the stacking fault. This width will be maintained. It is not going to decrease, and as a result of that, the dislocations will find it difficult to move, right? So this is one of the mechanisms by which the solute atoms can restrict the movement of dislocations by getting segregated along this stacking fault, which is present in the gap between the partials. Like you have elastic interaction and the attraction between opposite stress field, you can also have electrical interaction where there can be attraction between oppositely charged species, electrical species. Okay, because like how you have stress field in the dislocation core, you also have a dipole in the dislocation core. So this dipole will have a positive and negative end, and therefore the positive end will attract the negative portion of the lattice that is resulted due to the presence of the solute atoms, and the positive part on the other hand similarly will attract the negative portion of the lattice due to the presence of solute atoms, right? So that is what is known as electrical interaction, because you also know that solute atoms, apart from size difference, there is one more difference. Solute atoms have a different valency. So while the elastic interaction arises due to the size difference, here the electrical interactions arise due to the valency difference, because due to the difference in the valency, the charge will be concentrated around the solute atoms, and that is how it will give rise to positive and negative ends, and that will be attracted by the dipole which is present in the dislocation core, right? As I said, the positive charge will be attracted to the negative end of this and vice versa, and that is how the solute atoms will again get attracted to the dislocation core and will restrict their movement, right?
So with that, we come to the end of this particular lecture, and the rest of the things that we have on this topic will be taken up in the next lecture. So I'm going to stop here today. Thank you for your attention.